Hi students, today we are going to discuss class 2 mathematics chapter number 1 real numbers. Before we are going to discuss what are real numbers, let's take a quick revision among different types of number systems. First, we learn natural numbers. Natural numbers starting from 1, 2, 3, etc. to infinity. Similarly, when we add a 0 to the natural numbers, we will get a set of whole numbers 0, 1, 2, 3, etc. to infinity. After natural numbers and whole numbers, the next integers. What are integers? Integers is a sum of whole numbers and negative of natural numbers. That is minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. After integers, then next we learn fractions. What are fractions? For example, you are provided with a cake and they are divided into 4 equal parts. And if you took one piece among that 4 equal, then how much you got? That means 1 by 4th. Okay, these types of numbers like minus 5 by 3, 5 by 3, etc. These types of numbers are called fractions. And finally, we learn rational numbers. What are rational numbers? The definition says that a number R is called a rational number if it can be written in the form P by Q, where P and Q are integers and Q should not be equal to 0. These are called rational numbers. That means any number we can represent in the form P by Q, then these numbers are called rationals. For example, 2 by 3, 5, 3 by 2, these all are rational numbers. Even 6 also a rational number because 6 can be written in the form 6 by 1, where in this case 6 equal to P and 1 equal to Q. And finally, we learn another kind of numbers which are called irrational numbers. Irrational means it is just opposite to rational numbers. That is, a number S is called irrational number if it cannot be written in the form P by Q. So P and Q are integers and Q should not be equal to 0. These types of numbers are called irrational numbers. For example, square root of natural numbers, root 2, root 3, etc. root 5. These all are irrational numbers. Pi is an irrational number. The decimal expansion of pi is 3.14, etc. So these are called irrational numbers. And finally our question is, what are real numbers? Real numbers is nothing but just a collection of rational numbers and irrational numbers together. That means a real number in which we can represent on number line. These are minus 5 by 3, root 2, pi. These all are real numbers. Whether it is irrational or rational, these all are real numbers. Now my question is there any other kind of number system other than real numbers? Yes, let's take an example. What is root 4? Root 4 is equal to plus or minus 2. And what is minus of root 4? Which also plus or minus 2. Then finally, what is square root of minus 4? We cannot find the square root directly because these are not real numbers. Euclid division lemma. It says that given two positive integers a and b, then there exist unique integers q and r satisfy a equal to pq plus r, where r greater than or equal to 0 and less than b. Let's take an example. Let A equal to 21 and B equal to 4. Divide it. 21 divided by 4, which is equal to 5. 20, remainder is 1. So we can write 21 is equal to 4 into 5 plus 1, where 21 is the dividend, dividend, and 4 is the divisor, and 5 is the quotient, and 1 is the remainder. Clear? So this is what we call as Euclid division level. Any number we can represent. The necessary condition is that R should be greater than or equal to 0 and less than B. This is the range of remainder. That's all. Let's start to solve exercise questions. Exercise 1.1, question number 1. Use Euclid division algorithm to find the HCF of 135 and 225. So, since 135 is less than 225, we need to proceed with the long division method. So, divide 225 by 135. What do we look at? Quotient is 1 and 1 into 135 is equal to 135. Subtract it, 0, and finally 90. 90 is the remainder. So in first algorithm, 225 is the dividend, 135 is the divisor, 1 is the quotient, and 90 is the remainder. Again, in next step, the 135 will be the dividend. Divided by 90, we will get a quotient as 1. Again 1 into 90, 90. Remainder is 45. Again, in the third algorithm, dividend will be 90. What we will get a quotient as 2, and 2 into 45 is equal to 90. Remainder is 0. So usually we will get HCF as 45 from the long division method. Now we can write the algorithm for this. 225 is equal to 135 into 1 plus remainder is 90. Okay. Then second algorithm, this will be the dividend. 135 is equal to 90 into 1 plus remainder is 45. Again, in the third algorithm, 90 is equal to 45 into 2 plus remainder is 0. So according to Euclid division algorithm, in which step we will get a remainder as 0, the corresponding divisor will be the HCF. So that is HCF of 135 and 225 is equal to 45. Okay. And one more thing we will get from these steps. We find HCF of 135 and 225 as 45. Similarly, HCF of 90 and 135 is also 45. As well as HCF of 45 and 90 is also 45. This concept also you need to remember to solve some other kind of problems. Exercise 1.1, question number 2. Show that any odd positive integer is of the form 6 cube plus 1 6 or 6 cube plus 3 or 6 cube plus 5, where q is some integer. So we need to express in the form 6 cube plus 1 or 6 cube plus 5 or 6 cube plus 3 or 6 cube plus 5. So in this expression, divisor is 6. So let's take b is equal to 6. Apply Euclid division lemma. What is it says that a equal to b cube plus r, where r greater than or equal to 0 and less than b. Since b equal to 6, r will be 0, 1 or 2, 3, 4 or 5. It cannot be 6 because it should be less than b. That means remainder should be less than 6. So the numbers are a equal to 6 cube plus 1, 6 cube plus 2, 6 cube plus 3, 6 cube plus 4 and 6 cube plus 5. Here remainder is 0. When r equal to 0, 6 cube plus 0 equal to 6 cube. That's all. Now, looking these numbers, 6 cube plus 2 and 6 cube plus 4. Here, 6 cube plus 2, that we can write as 2 into 3 cube plus 1, and 6 cube plus 4, that we can write as 2 into 3 cube plus 2. For these numbers, 2 is a factor. 6 cube can be divided by 2, 6 cube plus 2 can be divided by 2, and 6 cube plus 4, that also can be divided by 2. That means these integers are even integers. Then what are the remaining integers? Let's write it. These are even integers. So 6 cube plus 1, 6 cube plus 5 and 6 cube plus 3 and 6 cube plus 5 are odd positive integers. Exercise 1.1, question number 5. Use Euclid division lemma to show that cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. So here we need to prove in the form 9m or 9m plus 1 or 9m plus 8. So you might be thinking that here we can take b equal to 9. Of course we can take, but if you take b equal to 9, we need to take the cube of all the integers. Almost 8 integers will be there. So instead of that, we can take b equal to 3. Why b equal to 3? Because when we take the cube of 3, it is equal to 27, where 27 is a factor of 9, we can take 9 outside. Now, according to Euclid division lemma, a equal to b cube plus r, where r greater than or equal to 0 and less than b. Since r equal to b equal to 3, remainder will be 0, 1 and 2. Therefore, the integers are a equal to 3 cube plus 1 or 3 cube plus 2. Now let's take the cube of this integer. First, when a equal to 3 cube, a cube is equal to 3q whole cube, which is equal to 27 q cube. 3 cube is equal to 27 and q cube is equal to q cube. And 27 we can write as 9 into 3 and q cube, which is equal to 9m, where m is considered as 3q cube. So first we represented in the form 9. Similarly, we are going to take when a equal to 3q plus 1. That is a equal to 3q plus 1. We will get a cube is equal to 3q plus 1 whole cube. A cube is equal to 3q plus 1 whole cube. Here it is in the form of x plus y whole cube. Apply that identity to expand this whole cube. We have x plus y whole cube is equal to x cube plus y cube plus 3xy into x plus y. Apply this identity here, we will get a cube is equal to x cube, that is 3q whole cube, plus y cube will be 1 cube, plus 3 into 3q into 1, 3xy, 3 into 3q into 1 plus into x plus y, that means 3q plus 1. A cube is equal to 3q whole cube we already written in the form here, 9 into 3q cube. That is 3q whole cube is equal to 9 into 3q cube plus 3 into 3q, 9q into 3q plus 1 plus 1. Here 9 is common in both terms. So taking 9 outside, 9 into here remaining 3q cube plus 3q plus 1. Sorry, 9 is taking common outside, 3q cube plus q into 3q plus 1. Close the bracket. Plus 1 is outside. Now taking 3q cube plus q into 3q plus 1 as m, we will get the expression as 9m plus 1, where m is equal to 3q cube plus q into 3q plus 1. So here we represented. Now maybe you ask, here, why here m is equal to 3q cube and here m is equal to 3q cube plus q into 3q plus 1? Because in the question it is mentioned q for some integer m. There is m is not a specific integer. M can be some integers. Clear? Similarly, you can take when a equal to 3q plus 2, take whole cube and apply this identity, you will get in the form 9m plus 8. That's it.